Let me explain the objectives of the CRC Research Center's Googie drone research. Googie drone is a circular-shaped drone with a coaxial reverser drive that performs 4 functions. First, we take the evidence of the incident site that requires scientific investigation and proceed to 3D restoration based on the collected images. The 3D reconstructed data enables remote analysis by investigators. Also, it is effective for investigation by viewing the preserved data. Second, it is a citizen-friendly design. Googie drone has a rotating propeller inside and a shock absorber material is installed on the exterior panel. It prevents accidents caused by propellers and is suitable for the elderly and women returning home to dark alleys. The third function is suspect tracking and suppression. With the installed camera and tracking algorithm, you can remotely track suspects and subdue them using tear gas and taser guns. Googie drones assist police officers safely and efficiently. The last function is toxic gas detection and tracking. A sensor capable of detecting explosives and a direction detection algorithm enable identification of low concentration gas molecules. It is possible to select the types and sources of unidentified explosive substances and minimize the loss of human and material resources. The Googie Drone Research Team. Let me introduce the Googie Drone Research Team. Professor Im Jung-yeon, the head of the center, and professors and student researchers of mechanical engineering are participating. This is the development of the Googie drone. First is the hydrodynamic design to increase the thrust of the drone and the lightning width topology optimization. We are extracting optimized models with airfoil designs that maximize the Coanda effect and optimal design for lightning. We are conducting basic research on new materials that can transform the appearance by function with smart materials using shape memory alloys. We are also researching sound-absorbing materials to improve drone noise. The goal is to produce a sound-absorbing effect and strong thrust with a rigid but thin blade design. In this study, we developed a shape memory textile composite capable of large multimode actuations. We use this to create shell-like morphable structures. To fabricate the shell-like morphable structure, we embed multiple SMA wires in a soft polymeric matrix. Each woven composite exhibits multimodal deformation. The direction of actuation is based on the composite laminate design. To evaluate the performances of different shape memory textiles, we designed and fabricated soft morphing shell composites using different laminates. Finally, we used motion tracking cameras to evaluate the characteristics of three-dimensional deformation. Based on the shape memory alloy and shape memory polymer, we developed a morphing flap of UAV. The soft actuator is capable of shape retention, which can maintain a deformed state without additional energy based on its stiffness change characteristics. The use of the soft composites that are placed within the soft polymeric matrix allows deforming the rear section of the wing such that it is possible to change the aerodynamic properties. The actuator consisting of soft composites allows the soft morphing, which is producing a smooth deformation continuously. The retention capability of the soft morphing actuator is accomplished by the phase transformation of the embedded SMP composites, which can retain the geometry of the wing structure between non-deformed and deformed stature by the SMA actuation, without continuous energy consumptions. The morphing flap is integrated into the wing structure of a UAV, and wind tunnel experiments conducted to observe its aerodynamic performance and structural stability. From now on, let me show you the structural design of our Googie drum model, particularly based on the numerical simulations. Basically, we are trying to perform the numerical simulations in two different ways to achieve our goal, which is developing a new design that fits to the ducted coaxial drum model. In fact, researches on these kinds of coaxial drones are not performed much since the coaxial drones have some weak points, but we adapted the design as we have a specific purpose related to the policing, guard, and safety. So first of all, we focused on the lightweight design considering the structure topology optimization. The objectives are minimizing the weight of the drone, maintaining the structural safety. So the objective function was set to the maximization of the stiffness of the drone structure. Here, in this right figure, we selected the upper frame to be designed and applied some boundary conditions corresponds to the coaxial model. As the constraints of the design, the volume fraction was set to be 30% of the initial design, and we assume that the battery and the electric devices are installed on the top of the drone frame. As a result of the optimization, we obtained some designs. Actually, we did not expect those optimal designs. However, we did not adopt these designs because the design was not easy to manufacture even though we used the 3D printers with high resolutions. Some parts should be simplified, but then there is actually no difference between the optimal design and the original model that we've designed based on our experience. In fact, basically, the feasible design space was too narrow because the structure of the ducted coaxial drone is not complicated, so we changed the direction of our research for the shape optimization of the duct. And we expect that there might be some particular designs which is optimal for the coaxial drone. And we also want to figure out the optimal parameters, for example, the distance between two propellers or related rotating speeds of the props. So, in the second approach, we are going to perform the CFD simulation for the coupled aerodynamics and structural design. Actually, the CFD simulation for this problem is really heavy, so we are going to use the DOE-based surrogate modeling approach. So then we expect that we can get some particular shape of the drone that maximizes the thrust. For the CFD simulation of the ducted drone, we adapted the actuator disc conditions, which is one of the most popular and convenient way for modeling of the propellers. Here is the basic procedure. From the given problem, we first generate the fan using conventional CAD software. Then we import the model to the commercial CFD program. After that, we can generate the mesh structures of both disk and the whole domain. And then, by imposing the solving conditions, we can get the results as presented here. So, with this modeling technique, we performed CFD simulation in order to check whether the ducted drum models can be accurately analyzed or not. At the first stage, we only considered the single rotor case, but the geometric properties are given here. And the geometric properties are given here. For the turbulent model, we adopted the K-epsilon RNG model. And I'm going to skip for the details anyway. We checked all the results in details and compared those reported in the literature. And as shown in this pressure distribution, we can observe the thrust at the bottom of the drone. In this figure, the positive pressure is plotted in red, and that means there exists a reaction force applied in an upward direction. Also, both vertical velocity component and the velocity vector fields show reasonable distributions. In our research group, it was the first time to simulate these kinds of a drone structure using the CFD turbulent model. That's the reason why we started the analysis for the single rotor case first. And we actually finished the verification of this analysis for the single rotor model. We are going to extend this model with two actuator discs for the simulation of the coaxial drone. And then we are planning to generate a surrogate model after performing multiple heavy CFD simulations. Then we can optimize the shape of the drone by using the DOE-based optimizations. In fact, finding the optimal shape of the coaxial drone is a new research in this field. So we expect that we can publish some good papers including the comparing the simulations with the experimental results.